Hello everyone, welcome to the lecture again. In the last lecture, we talk about the beam and distributed forces. Today, we are going to talk about the flexible cable. Now, these cables can also support various kind of loads. For example, it can be a distributed load or it can be a continuous load. So, a cable is specifically flexible cable. In these cable, the bending is of course allowed. And the force in the cable is always in the direction of the cable. Okay. So, as I said, these cables can support various concentrated loads or continuously distributed load. For example, these cables are used in suspension bridges, in aerial tramways, in transmission line, and so on. Okay. So, we will discuss two cases of this cable. In the first case, the cable will carry a uniform distributed load along the horizontal axis. So, we have a cable carrying a uniformly distributed load along the horizontal line. Okay. And in this case, we will consider that the mass of the cable is negligible compared to the load that it is carrying. So, for example, we can have a bridge and this bridge is supported by this cable. Let us say the weight of these cables is negligible compared to the weight of this bridge. In that case, if I move along the x direction, then this cable is supporting a uniform load. Now, the second case will be the cable carrying a load that is uniformly distributed along the cable itself. Okay. So, for example, we can have a cable which is hanging under its own weight. In this case, the weight is uniformly distributed along the cable. Okay. Now, to analyze this, let us start with a general case. So, let us say I have a cable and this cable is hanged between these 2 points, and let us say on this cable there are some non-uniform load which is applied. Let us say W is the load intensity. So, it will be Newton per meter unit, and of course, this W is a function of x, where x is the horizontal direction, or this W is a function of s, where s is along the cable. Okay. So, to analyze it, let us say we consider a differential element dx, which is at a distance x away. So, the weight of this differential element will be w dx. So, to analyze this cable, let us zoom this part. So, we have this part, its weight is w dx, and from the origin it is at a distance x, and let us say at this general position x, the tension in the cable is T, and let us say the cable makes an angle theta with the horizontal. So, therefore, over here it will make a angle theta, and at x plus dx, let us say the angle is theta plus d theta. Over here the tension in the cable is T, and here let us say the tension is T plus dt. Now, on this infinitesimal portion we can apply the equilibrium condition. So, let us use the force balance equation, summation f x equal to 0. So, this will gives us T plus dt cos theta plus d theta equal to T cos theta, and if we use the force balance in the y direction, then summation f y equal to 0 will give you T plus dt sin theta plus d theta equal to T sin theta plus w dx. Now, on the left hand side we have cos theta plus d theta, which we can expand as cos A plus B equal to cos A cos B minus sin A sin B, and in the second equation we have sin A plus B equal to sin A cos B plus cos A sin B. So, now let us expand this. So, we have T plus dt cos theta cos d theta minus sin theta sin d theta equal to T cos theta, and we have T plus dt sin theta cos d theta plus cos theta sin d theta equal to T sin theta plus w dx. Now, under the condition that theta is small, sin x can be approximated as x and cos x can be approximated as 1. Now, under the approximation that d theta is small, we can approximate sin d theta as d theta and cos d theta as 1. Let us put it back above. So, we have T plus dt cos theta cos d theta becomes 1 minus sin theta, and sin d theta becomes d theta equal to t cos theta, and we have t plus dt sin theta, cos d theta becomes 1 plus cos theta d theta equal to t sin theta plus w dx. Now, let us multiply that. So, we have t cos theta minus t sin theta d theta plus dt cos theta minus sin theta dt d theta equal to t cos theta and t sin theta plus t cos theta d theta plus dt sin theta plus cos theta dt d theta equal to t sin theta plus w dx. Now, since d theta and dt they are small, so therefore, let us drop dt d theta because that will be even smaller. So, this term we can neglect and this term also we can neglect, and here t cos theta will get cancelled with this t cos theta and t sin theta will get cancelled with that t sin theta. So, we have minus t sin theta d theta plus dt cos theta equal to 0 and t cos theta d theta plus dt sin theta equal to w dx. Now, these two equations can be written in the following manner. So, this can be written as d t cos theta equal to 0 and d t sin theta equal to w dx. Here you can use this t as first function and cos theta as second function, and you can differentiate, you will get the above equation. Now, what is t cos theta? T cos theta, so let us look at this equation. T cos theta is the horizontal component of t, and if its differentiation is 0, that means it is constant. So, the above equation tells me that the horizontal component of t is constant. Let me repeat again, t cos theta is the horizontal component, and if its differentiation is 0, that means it is constant. So, therefore, t cos theta is constant, let us call it t naught. Now, let us look at this equation. This equation tells me that d and t I can replace at t naught over cos theta from here, and then we have sin theta equal to w dx, and sin theta over cos theta is tan theta. So, therefore, I can write it down as d t naught tan theta equal to w dx, but we know that tan theta is nothing but slope. So, this is dy by dx. So, I can write down as d t naught dy by dx equal to w dx. This dx I can put on the left hand side and I will get d2y over dx square equal to w over t naught. Let us call it equation A, and this is the differential equation of flexible cable. Note that here t naught is the horizontal component of t and it was t cos theta. Now, let us discuss the first case where the intensity of the vertical loading is constant. So, case 1 where the intensity of vertical loading W is constant. So, let us say you have some load W, and this load W is held by this cable at 2 points A and B, and I have considered the general case wherein this A and B, they are not in the same horizontal line. So, let us say the cable is suspended from 2 points A and B, which are not on the same horizontal line. And also let us place our coordinate axis at the lowest point of the cable. So, let us say this is the lowest point, I am going to put my coordinate axis over here. So, this is y axis and this is the x axis. Okay. So, we placed the coordinate origin at the lowest point of the cable. Okay. Now, let us say the height of point A is h A and the height of point B is h B. This distance is S A and this distance is S B. Similarly, let us say this length is L A and this length is L B. And as I said, W is the load per unit horizontal length and it is constant. Now, here we have neglected the mass of the cable because the loading is much larger than the weight of the cable. So, to analyze this problem, let us start with equation number A because that was the general equation and here W is constant. So, to find out the equation of the cable, let us integrate equation number A. So, integrate equation A. So, we have dy by dx equal to W over T naught x plus a constant C. Now, this constant C we can determine from the boundary condition. For example, you can see that at x equal to 0, that means at this point dy by dx or the slope is 0. So, if we put it back over here, then we immediately get C equal to 0. So, therefore, we have dy by dx equal to Wx over T naught. Now, again integrate it. So, if we again integrate, then we have dy equal to Wx over T naught dx. So, integral dy will be Wx over T naught dx and y is varying from let us say 0 to y and x is varying from 0 to x. So, we have y equal to W x square over 2 T naught. And what is this? This is the equation of parabola. Let us call it equation number 1. So, under constant vertical loading, the equation of the cable will be the equation of parabola. Now, let us calculate the tension in the cable. And for that, let us look at the free body diagram. So, we have the x axis, we have the y axis, and take the portion of the cable which is up to x distance away from the origin, and the tension T is going to act in the direction of the cable. So, let us say it is making an angle theta. So, therefore, the horizontal component will be T cos theta, which is of course T naught, and it is constant, and let us say the length of the cable is S. So, its weight will be W times x, and it is going to act at a distance of x by 2. So, now let us calculate T. T will be square root T x square plus T y square, and T x is constant, it is T naught, and from the free body diagram T y will be W x. Let us put it back. So, I have T equal to T naught square plus W square x square. Let us call it equation number 2. Now, using the boundary condition, we can eliminate T naught. So, let us use the boundary condition. Let us use at x equal to LB. So, let us look here at x equal to LB, we have y equal to HB, and we can also use equation number 1, which is the equation of parabola. So, we have HB. So, let me just write down this equation. So, we have y equal to W x square over 2 T naught. This was our equation number 1. Let us put y equal to HB. So, we have HB equal to W LB square over 2 T naught, and from here I can find out what is T naught. So, T naught will be W over 2 HB into LB square. Let us put it in equation number 2. So, we have T equal to W x square plus LB square over 2 HB square. Let us call it equation number 3. Now, you can see here for T max my x has to be maxima, and what is the maximum value of the x here? The maximum value of the x is LB. So, from here I can also find out what is T max. So, for maximum T my x should be LB. So, therefore, T max will be W times LB 1 plus LB over 2 HB square. Let us call it equation number 4. So, this will be the maximum tension in the cable. Now, let us calculate the length of the cable. For that, let us calculate SB. So, SB will be 0 to SB ds, and ds will be square root dx square plus dy square, and this can be written as 0 to LB square root 1 plus dy by dx whole square dx, and dy by dx I can calculate from the equation of the parabola. Remember, y was wx square over 2 T naught. So, therefore, dy by dx will be w 2x over 2 T naught, 2 will get cancelled. So, we have 0 to LB square root 1 plus wx over T naught whole square dx, and this I can just rewrite as 1 plus wx over T naught whole square to the power half dx, and under the condition that wx over T naught is small, I can expand this. 1 plus x to the power n is 1 plus nx plus n minus 1 over factorial to x square plus so on. So, we will have 0 to LB 1 plus w square x square over 2 T naught minus w to the power 4 x to the power 4 over 8 T naught to the power 4 plus so on dx, and now we can very easily integrate this. So, it will be LB 1 plus W square LB square over 2 into 3 T naught square minus W to the power 4 LB to the power 4 over 8 into 5 T naught to the power 4 plus dot dot dot, or SB will be LB 1 plus 2 by 3 HB over LB minus 2 by 5 HB over LB to the power 4 and so on, wherein we have used T naught equal to W LB square over 2 HB. So, in this class we have discussed the case where the loading was uniform in the x direction or in the horizontal direction. In the next class we will analyze the case where the loading will be uniform along the cable. With this, let me stop here. Thank you.